Okay, so last question in paper 1 was the sequences one. I think you were just bamboozled by algebra here. You're quite good with arithmetic and geometric sequences, so again, there was no reason that you couldn't have done well. You just panicked, I think, because it was a lot of letters rather than numbers. But there's no reason for that, okay? So we're basically told that UN is an arithmetic sequence with first term equals A and common difference of D. Well, the first thing that tells me is that we know UN has nth term A plus n minus 1 times D. That's a formula you should know. It's in the formula book. It's easy, okay? And it says Vn can be defined as 2 to the power of u to the n. So Vn, therefore, is equal to 2 to the power of A plus n minus 1 to the power of D. Okay? What we've got to do is show that V of n plus 1 over V of n is a constant. Okay, so let's work out what that is. So V of n, we already know what that is. We just said it. It's 2 to the power of A plus n minus 1 D. Well, V to n plus 1 is you're going to replace n with n plus 1, so it's going to become 2 to the A plus n D. Okay? Now, rules of indices come into play. We've got the same base, so that can become 2 to the power of A plus nd minus A plus n minus 1 D, which is 2 to the power of A plus nd minus A plus nd minus D, which will cancel out to 2 to the power of negative D. Positive D, isn't it? Because it's negative. Okay? Because essentially you're going to get A minus A, which is nothing, ND minus ND, which is nothing, and minus D is positive D. And since D is a common difference, it's always the same, it therefore must be constant. Therefore, constant. Now, we should now also be able to work out the first term of this sequence. So that's V1. Well, that just happens when n is equal to 1. Well, if n is equal to 1, well, 1 minus 0 is nothing. Nothing times d is nothing. So it's just going to become 2 to the power of a. Now, write down a formula for Vn in terms of A, D, and N. Well, what type of series, or what type of sequence rather, is V of n? That's always what you've got to ask yourself. You're told that UN is arithmetic, and actually you should have realised by now that Vn is geometric, because basically if I do one term divided by the other term, I always get the same value, 2 to the power of D. So it must be a geometric sequence. But if it's a geometric sequence, remember, geometric sequence is always UN is equal to A times R to the power of n minus 1. A is the first term, so that's 2 to the power of A. R is the common difference, which we worked out as 2 to the D, to the power of n minus 1, which is equal to 2 to the A times 2 to the n minus 1 D, which is equal to 2 to the A plus n minus 1 D, which we already knew anyway. So we've got sort of two ways of showing that that is the case. Okay? So again, entry into this question is not too hard. What's coming next is more difficult, but if you really understand these formulas, you understand what a geometric series is, which is where you have a common ratio. There should have been no reason why that was difficult. Okay? So let Sn be the sum of the first n terms of the sequence Vn. Find Sn in terms of A, D, and n. So we've now established that Vn is a geometric sequence. So the sum follows the formula here, A times R to the n minus 1 over r minus 1. Well, again, we already knew that the first term was 2 to the a. We know that the common ratio is 2 to the power of d. And so we're going to get 2 to the d minus 1. Okay? And that should be 2 to the d to the power of n. So we can simplify that. We're going to get 2 to the a times 2 to the nd minus 1 over 2 to the d minus 1. Okay? And I don't really think that you need to do any more than that, because you've sort of done what it asked for. Okay? It says find Sn in terms of a, d and n. That's what you've done. So you might be able to simplify it, but why bother when the question doesn't ask you to? Okay? Right, find the values of d for which sigma between I equals 1 to infinity of vi exists. So that's asking you, when does the sum to infinity exist? And you should know a fact that the sum to infinity exists when the common ratio is between 1 and minus 1. So when the common ratio is between 1 and minus 1, we'll get a sum to infinity. If it's outside of that range, then we won't get a sum to infinity. So what we're basically saying is, when is 2 to the d less than 1 and less than minus 1? Okay? Now, the way I thought about solving that was just graphing it, really. I know what the graph of y equals 2 to the x looks like. It will be something like this, where this point is 0, 1. Okay? So I know that my value of d, or if we make this the y-axis and this the d-axis, I know that my y values are only allowed to be between 1 and minus 1. Well, that doesn't happen over here, but it does happen over here. So I know that d has to be less than 0 for there to be a sum to infinity. Okay? We could do it through logs. When's 2 to the d less than 1? Well, that suggests that when d is less than log base 2 of 1, which is when d is less than 0, and when is minus 1 less than 2 to the d, well, that would suggest that log base 2 of negative 1 is less than d. Well, that's not possible. We can't have a negative log, so hence we're sort of going to negative infinity there. Okay? So d has to be less than 0 for there to be a sum to infinity. Okay, so now we have to write the sum to infinity in terms of a and d. I hope that was in the test. I don't know why that's got removed. Hopefully would have assumed it anyway. So the sum of infinity is equal to a over 1 minus r. So it's a was 2 to the a, the 1 minus r, which is 2 to the d. Okay, now, so that's an easy mark there. Given that the sum to infinity is equal to 2 to the a plus 1, find the value of d. So when is 2 to the a plus 1 equal to 2 to the a over 1 minus 2 to the d? Well, quick rearrangement. 1 minus 2 to the d equals 2 to the a over 2 to the a plus 1. Rules of indices. 1 minus 2 to the d equals 2 to the a minus a plus 1. So 1 minus 2 to the d equals 2 to the negative 1. Sorry, that being too quick. 1 minus 2 to the d. So 1 minus 2 to the d equals a half. So 2 to the d equals, so take that over, that's going to be equal to 1/2, so therefore D equals -1. And the job is done. So I think A and B of question 11 wasn't really that difficult. You probably just bamboozled with language, an algebraic question rather than a number-based question. But, you know, it shouldn't matter. Really shouldn't matter. Should still be able to do it. This is a difficult question. So we're told we've got a geometric sequence with first term equal P and common ratio Q. So Wn, we can sort of work out what that's going to look like. It's going to be P plus PQ plus PQ squared, so on and so forth, to PQ to the power of n minus 1. Okay, that's what Wn will look like. So Zn is the log of that. Then that's going to be log P plus log PQ plus log PQ squared up to log PQ to the power of n minus 1. Now, you are basically asked to find the sum of the first n terms of Zn in terms of n, p and q. So the first thing you need to do is work out what type of sequence is it. You know, it's obviously either going to be arithmetic or geometric because you don't know how to do sums of any other types of sequence. So you should, common sense should have led you to think, is it arithmetic, is it geometric? And you can test, all you need to do is find out, if it's arithmetic, there'll be a common difference. If it's geometric, there'll be a common ratio. Well, let's find out if there is a common difference. So we'll do one term, log PQ minus the term before it, log P, equals log PQ over P equals log Q. Okay, so that's the difference between the first two terms. Third and second term will be log PQ squared minus log PQ, which equals log PQ squared over PQ, which is log Q. You can see the logic that we've got a common difference. Okay, if I subtract one term from another, I'm always going to get log Q. So this is an arithmetic sequence. And how do we find the sum of an arithmetic sequence? It's n over 2 times 2a plus n minus 1 times the common difference. So n we don't know, we'll just leave that, n over 2. A we do know is log p, so that's going to be 2 log p plus n minus 1 times the common difference, which we just established was log q. So let's try and simplify this. We have to try and reduce this to a single logarithm. So it's going to be n over 2 times 2 log p plus n log q minus log q. Let's just go up here, which is equal to, I'm going to get n log p plus n squared over 2 log q minus n over 2 log q. Okay, so that's going to be log p to the power of n plus log q to the power of n squared over 2 minus log q. Pen's died. My pen's died.